So good afternoon, everyone. My name is Francesco Petruccione, and I'm the interim director of NITheCS. And today we have the second lecture in the mini-school series that Jan, Joel, David is teaching. Yeah, and today we have the second installment of the practical introduction to quantum computing. Yeah, last week was mainly devoted to the general setup, and I think today it's getting a little more interesting with some non-trivial implementation of very interesting quantum mechanical situations. Yeah. So without further ado, Jan, people are here to listen to your wisdom. Yeah, you're most welcome to start, and I will slowly admit the people that are joining late. Yeah, so please, Jan, over to you.
Okay, thank you, Prof. Good afternoon to everyone here. I think just as a quick recap, last week we went through just some basic Qiskit functions for single qubit quantum computing, some operations you can do on single qubits, and you know, how to use the simulators and interpret the results, etc. And I think this week it will be very interesting to move on to 2 qubits and 3 qubit examples, and the functions and the gates that are available to us for 2 and 3 qubits, how to interpret the results, and then maybe we will look at some an implementation of a very simple sort of quantum algorithm. And that's the quantum teleportation scheme. I use algorithm in inverted quotes, but you know, it's we'll look at how to implement that with Qiskit, and we'll see how we can do some quantum teleportation. So I'm going to turn off my camera just to save some bandwidth, and I'll start sharing my screen. Okay. I hope everyone can see my screen. So the first thing we're going to do today is we're going to look at 2 qubit gates. So again, I'm making the assumption that you've watched the previous mini school on quantum computing at least, or you have some experience with quantum computing, and or even quantum mechanics, in which you might be familiar that if you have 2 quantum systems, we can describe the total system by taking the tensor product of the state vectors that describe each subsystem. So for example, for 2 qubits, if you have 2 state vectors that describe each single qubit, then the total system of 2 qubits is described by the tensor product of those 2 state vectors. And in some cases, and as we'll see as we go further along, it's not always described as just a tensor product of 2 of single qubit states. Sometimes we have cases where the total state vector for our Hilbert space of dimension 4 cannot be written as a product state, in which case we have entanglement. So we'll talk a little bit about that as we go through the first part of this lecture. So I'm going to start off with 2 qubit gates. The imports you should all be familiar with by now. We're just going to import Qiskit and the air simulator, as well as NumPy and SymPy. This is going to allow us to just do the printing of some of the state vectors that we get very nicely and easy to read. So, of course, when we look at 2 qubit operations, we need to look at the most simplest 2 qubit operation we can think of, and that would be the controlled NOT gate. And of course, last week we've seen the NOT gate, which took the qubit from state 0 to 1 and 1 to 0. But what will happen if we have 2 qubits and we wish to control the application of this NOT gate on a qubit using the state of another qubit itself? And that's how we get the C0 gate. And the reason this gate is so important is because along with the single qubit gates that I showed you last week, like H, T, S, as well as the Pauli gates, these form a universal set. And this means that we can take any operation, unitary operation on our qubits or system of qubits, 2 qubits, n qubits, whatever, and we can always decompose that operation into just products of these single qubits and C0 gates. This is a very important gate in quantum computing. And if you're interested in how you do these decompositions, I would advise you look at the Solovay-Kitaev theorem. You can see a proof of that in Nielsen and Chuang, or you can just look at some of the original papers. But for now, I'm just going to talk to you about just the C0 gate and how to use it in Qiskit. So let's consider our 2 qubits being in this initial state where the first one is in the state 1 and the second one is in the state 0. We want to use that the first qubit controls whether or not we apply our NOT operation to the second qubit. So you can think of the C0 gate as like, analogous to like a sort of an if statement in programming. This is way we sometimes use it to teach the computer scientists in our course that Professor Patricio and I offer. And you can think of it as that if you look at the circuit down here, this C0 gate, the way we draw it, we have this closed dot on the control qubit, and we have this like sort of circle with a plus in it that signifies a NOT operation on the target qubit, or the qubit you intend to apply the NOT operation to. But the way you could think of this control NOT is that if the control qubit, so the if part is if the control qubit is in the state 0, then apply identity to your target qubit, which is the qubit you intend to apply the gate to. And if the control qubit is in the state 1, then apply the NOT operation to your target qubit. So to do this this very simple operation of the C0 gate to this state, we first need to construct this as our initial state. We remember from last week that for Qiskit, whenever we create a quantum register, and you see in this quantum register now, I have the parameter 2, meaning that there's 2 qubits in my quantum register. They're always initialized to the state 0, the state vector 0. And if we want to construct the state 1, 0, we'd have to apply X first just to the first qubit. And then we have this as our initial state. So that's what I do here in our quantum circuit, is that I just apply X to the first qubit in the register, and then I apply the C0. So this function applies the C0 gate to our circuit, and where the first parameter in this function is the control qubit, and the second one being the target qubit. So here I'm saying that the first qubit is my control, and the second qubit is the target. So to plot the circuit, we can see what it looks like in the circuit notation. You have an X here, and then you have a C0 here. This is a very simple circuit, but we can see that running the circuit, we expect that the result we obtain is just going to be the state 1, 1, because the first qubit is always the state 1. So we're always going to apply X to, there's no superposition here. So we're going to apply X to the 0, so we get 1, 1. And this is the state vector we expect to get. And we can execute it like we were familiar with from last week using the state vector simulator. And of course, when we print out the state vector, we use the SymPy matrix so that it prints it out very nicely. We see that we get the vector that we expect. So that's effectively, the most basic way we can use the C0 operation. And of course, if you were to switch the control and target qubits in the above example, you need to ask yourself what would happen. And the answer is that the state should remain the same, because if the second qubit is your control qubit, then you're not going to apply X to the first qubit, so you'll always be in the state 0 or 1. But it's interesting to see what happens if you switch these the control and target qubit. And you know what? Something that I say in this exercise is that you can effectively change your initial state. You can put in an arbitrary initial state, or you can have 1, 0, 1, or maybe just 1, 1, and you can see how does the C0 gate with the control and the target switched, how does that affect your state? And that's just an exercise you can try for yourself when you're working through this notebook. Now that we know about the C0 gate, we get to one of the most important features of 2-qubit operations, or something that comes up when you have more than 1 qubit in your system, and that is entanglement. And we know that entangled states are not separable. That means that you can't write them as a tensor product of 2 single qubit states. And we want to construct a very basic example of a very simple entangling circuit. So the most basic example will just be a Hadamard gate on your control qubit, and then you apply a C0. And this is one of the more famous entangling circuits because it produces something known as a Bell state. And this is going to allow us to see how we can construct a Bell state using Qiskit. Of course, this is also something to note, and that's that this state is also a maximally entangled state. So, if you're interested in maximal entanglement, then the belt state, this belt state here is maximally entanglement as well as other belt states. Okay, so to construct a very simple entangling circuit, all we need to do is we construct our quantum register and our quantum circuit with 2 qubits. We apply a Hadamard gate to the first qubit and a C0 where the control is the first qubit and the target is the second qubit. Now, what does this circuit do if we think about it in Dirac algebra or Dirac notation? Well, what will happen is the first qubit is in the plus state, so it's in a superposition of both 0 and 1. And what that tells us is that before we apply the C0, our 2 qubits are in the state 1 over square root 2 on 0, 0 plus 1, 0. So that means that when this first qubit is in the state 0, do nothing here. So half the time we'll just be left with the state 0, 0. But when the first qubit is in the state 1, then apply x to the second qubit. So half the time the first qubit is in the state 1. So what's going to happen is you're going to end up with 1, 1. And this produces the belt state that we expect. And you can see after running it, we get this state vector here. And the result of the state vector is the same as just having 0, 0 plus 1, 1 all over square root 2. And this is the first belt state. There are other belt states. So there's actually 4 belt states. And the exercise that I have here is going to give you some practice with constructing the other 3 belt states. So the idea would just be to apply the same circuit that we have above, but for these initial states here. And that'll construct the other belt states. And it's very easy to do in Qiskit because it's the same code. We're just changing the initial state. So what I do is I write a quick function which has this entangling circuit, the Hadamard and the control knot. And what I do is I just create the different initial states every time. So in the first case, we want the state 0, 1. So we just want to apply x to the first qubit in the second qubit in the register. And then, of course, you can just add the 2 quantum circuits together. When you use the plus symbol in Qiskit, it sort of is concatenating the 2 circuits together. So I concatenate my initial state with the entangled circuit where we use the same quantum register here. And we run the simulation. And what we get is we get the second belt state. And we repeat it for the different initial states. And what we end up with is the second belt state, which we see here. Sorry, this will be the third belt state. And as you can see, the initial state that we constructed here was 1, 0. So I just applied x to the first qubit and the code stays the same. And for the last one, all we need to do is make the initial state 1, 1. So we apply x to both qubits and we run the same code and then we get this belt state here. So also, if we wanted to construct an arbitrary entangled state, not something that looks like, 0, 0 plus 1, 1 all over square root 2, then we could do that using the U3 gate, which we learned about in the last week's lecture, to create an arbitrary superposition in our control qubit so that we have entanglement, but with an arbitrary sort of superposition. And the way we can go about doing that is we just use this U3 gate, or you can just use U, which is also acceptable depending on the version of Qiskit you're using. We have our 3 parameters and the qubit that you want to act it on. We put our C0 straight after our controlled U3 gate, and we get the state vector we see here. And here we have an arbitrary sort of superposition on the first qubit. So the entanglement isn't necessarily 1 over square root 2 on 1, 0, 0, 1. So that's what you can see here. There's also other types of controlled gates that you can get for 2 qubits. That they work in a similar way to the C0 gate. And the simplest ones we can think of will be the controlled Y gate and the controlled Z gate. And these are very, very they work very, very similar to the controlled NOT in the sense that if the control qubit is in the state 0, then do nothing to your target qubit. And if this is in the state 1, then apply the Y gate to your target qubit. The code for CY, the syntax rather, is just qc.cy. And the control qubit is always the first parameter, the target qubit being the second parameter. This is what the controlled Y gate would look like. And for the controlled Z, it's the same notation, except we use CZ instead of CY, but we use the same first parameter being the control and the second one being the target. And you might ask, but why is it that we don't have a box with a Z here? And so we can differentiate the control and the target. And well, if you've ever looked into Nielsen and Chuang or some other quantum computing resource, you'll see that switching the control and the target qubits in a controlled Z gate sort of leaves it invariant. So it doesn't really matter, if this is the control or that's the target, the action is the same. So you can actually try it. If you have the matrix representation for the controlled Z gate with the first qubit being the control and the second one being the target, then and you find a matrix representation for that, and then you switch the control and the target and you find the matrix representation for that new gate that you just did with the switch, you'll see that those matrices are the same. So, switching the control and target in a control Z gives you an equivalent gate. So we just have with both of them being the control. That's the notation that we see here. So, of course, the idea would be, to construct in Qiskit these circuits that make use of control Z and control Y, and use the following input states. And the idea would be to just, come up with some examples of circuits and just run them effectively. So all this is just doing is a little exercise that gives you some practice with working with control Z and control Y. And usually what we'd like to do is, if we're teaching this for the theory aspect of the course, is that the students would be asked to oftentimes, repeat the outcome of the circuit by hand using the Dirac notation, or even by just, doing it using some package that can do matrix multiplication like Mathematica or Python, like SymPy or NumPy. But in this case, we're just going to use Qiskit. We construct a circuit that makes use of control Z and control Y. We just put in these input states and run it and see what we get. This is just an exercise to just give you some practice with using the syntax and getting used to using Qiskit. So of course, I just make a very general circuit. It doesn't serve any particular purpose. I just put these gates in this sort of random sequence just to see, and get some practice with using these controlled Y and controlled Z. And of course, it follows the same principle. We just need to do a quantum register with 2 qubits, a quantum circuit, and we need to construct the following input states. So if the first qubit is in the state plus, what we need to do is we need to apply Hadamard to the first qubit, which you see here, and we append to that our circuit with the S and the control Y and the control Z, etc. And we run it. This is what our circuit looks like, and this is what the output looks like of this circuit. If we use the second input state, we needed to construct the state minus and 1. So the way we can do that is, the first thing we need to do is we will need to put both qubits in the state 1 and apply Hadamard to the first qubit, in which case you'll get minus and 1. And then we put our same circuit appended to this initial state. We run it. This is what the circuit looks like. This is what the output state vector looks like. Again, there isn't really a particular purpose of the circuit. It's just to demonstrate the syntax of the controlled Y and the controlled Z gate, and just to give you some practice with using the simulator for 2 qubits and outputting some state vectors. And it's the same thing with part C and D. We just change the input states and we add that circuit. You can play around with these functions if you're interested and just see what type of state vectors you can generate. The next part will be about drawing the U3 gate. So, we had so far, X, control Y, control Z, but what if we wanted to control an arbitrary operation? So we just wanted the most generic unitary, single qubit unitary, and we want to control that, and well, we use the CU3 gate. And what that does is you have your 3 parameters, and you can specify a control and a target qubit for this U3 gate. This is what it would look like here. And of course, you can use this to create or use this in your algorithms. Like for example, you could use this CU3 gate in doing amplitude encoding if you're doing some type of QML algorithm. This will allow you to entangle to an index register training points that you're going to feed into a quantum machine learning algorithm. So these are some of the very basic 2 qubit gates that you might come across when you're working with Qiskit. But what about a 3 qubit gate? What 3 qubit gates or 3-qubit circuits. What about those? How would we go about using these registers with 3 qubits, interpreting the results? Well, it's the same thing. All we're doing is changing 2 to 3 in Qiskit. And that's one of the beauty of using a Qiskit, is that it's very easy to just work with large numbers of qubits and very deep circuits, because Qiskit does a lot of the heavy lifting for you. So I want to go ahead and just construct this G at Z state. And this is an entanglement of 3 qubits. This is a 3-qubit entangled state. And this is what it looks like. And I want to construct a quantum circuit that will construct this GHZ state. So the way we go about doing that is we, of course, have our quantum register. And here we have a classical register because we're going to use the QASM simulator to prepare this, to create this state. And the first thing we do is we apply a Hadamard gate to the first qubit. And then we have 2 C0s that we see here. So we have 2 C0s. We'll have 1 C0 where we entangle the first qubit and the second qubit, and 1 C0 entangling the first qubit and the third qubit. We put in our barrier to separate preparation and measurement, and we measure all 3 qubits. We can run this on the QASM simulator, and if we execute the job, we see that we get counts such that, approximately half the time we're in the state 0, 0, 0, and approximately half the time we're in the state 1, 1, 1 of the 1,000 experiments that we performed in the simulation. Of course, you can get closer to half by increasing the shot count, but effectively the circuit that we've created here constructs this GHZ state. And you can, as an exercise, try to do the same thing, but with the state vector simulator. So that's just, some of the syntax and notation that you need when you're working with 2 qubits and 3 qubits in Qiskit, and this extends to many qubits as well. There are more advanced features of Qiskit, but of course you can look into the documentation for more information about the more advanced tools when working with many qubits. But for now, these are the most basic tools that you need to get started. So at this point, I would just like to ask, are there any questions? Okay, then if there
I don't see any questions in the chat so far. Yeah, but everybody, just a reminder to everybody, this is set up as a meeting, so everybody has the right to unmute themselves and ask questions at any time. Yeah, thank you.
Okay, thank you. If there are no questions, then I'll just move on. So this concludes the first part of the lecture, where we looked at just the syntax of using these 2-qubit operations, and also just looking at how to use this 3-qubit circuits and 3-qubit quantum registers. But what can we do with all of this stuff? So far, we spent 1.5 lectures just learning a lot of syntax and notation and a lot of basics, but we've not really done anything with our quantum computer, with our quantum simulator of a quantum computer. We've not really done anything so far where we've used this to actually perform some type of computation or even perform a certain task. And I think at this point, it's nice to move on to something that interests, I think, many people, and that is quantum teleportation. So quantum teleportation is a technique that they use to move quantum states around. And this is even in the absence of a quantum communications channel. So this was something you can look at if you see any resource on quantum computing. Quantum teleportation has to pop up in the introductory part of the book, or even lecture notes, etc. And the idea of quantum teleportation is very, very simple. You have 2 people, Alice and Bob. They're both spies, and they need to come up with some type of communications device that they can use to communicate with each other while they're in the field. So they figure that, okay, the best way to do this would be to actually use a quantum computer or use quantum systems to do it. So Alice and Bob both go off and they construct single qubits, and they entangle the qubits that they've constructed together, and they go off on their separate missions while only maintaining a classical line of communication with each other. So the whole goal of this would be they need to send messages to each other without getting detected. So you don't want somebody listening in on their messages so that they can complete their spy work safely. So the way they do it is they actually use the quantum teleportation protocol to do this. So Alice and Bob, they start off with their qubits, and when Alice wants to send a message to, okay, there's a question in the chat. Can you show how entangled qubits are related to the reality of quantum entanglement? Okay, I don't think I understand your question, but qubits are quantum systems. When we entangle them, it is just, we're doing quantum entanglement. That's what we're doing. They're interacting, and when they evolve into some state that's non-separable, then they're entangled. Quantum entanglement is a real thing. If you're interested in reading about that, I think you can pick up any good book on quantum mechanics. You can read about a lot of the experiments done by Bell, and you can read about Bell's inequality, and there's a lot of known information about quantum entanglement. But I will say that it is a real thing, and because qubits are quantum systems, entangling them is just the same as entangling two quantum systems, or entanglement in quantum mechanics. I hope that answers your question. I didn't fully understand the question, but if it's not clear, you can actually repeat yourself in the chat, and maybe I can give you a better answer. But okay, for now, I'll just proceed. Okay, so the idea was, again, I said that they entangle their qubits, and after they separate, the entanglement still holds true. If you have two quantum systems that are entangled, you can separate them by light years, and they're still going to be entangled. So they have these entangled qubits, and Alice wants to send a message to Bob. So what she needs to do is she gets another qubit, which she calls the message qubit, and she prepares this message qubit in some superposition state such that she encodes her message into this qubit rather, and she wants to actually send this information to Bob. So the way she would go about doing it is, the first thing that she does is she prepares her message in this superposition state here in psi, and what she does is she allows her message qubit to interact with one half of the entangled pair of qubits that she created with Bob. So with Bob and herself, Alice and Bob, they create this Bell pair, which you see here. And now she actually allows her message qubit to interact with one half of this Bell pair by applying the C0 gate. So the C0 gate that she will apply between the message qubit and her half of the Bell pair will create entanglement between her qubit and one half of the Bell pair. And she then goes and applies a Hadamard gate on the message qubit again. And after some algebra and factorization, which you can follow in this tutorial, she can choose to send Bob on the classical channel some outcomes. And she says, okay, Bob, if I got the outcome 0, 0, then you need to apply this operation to your qubit to get my message qubit. Or if you get 0, 1, apply this operation to your qubit to get the message qubit, and so on. So it'll all look a little more clear once you actually see the circuit to do this. And the circuit for doing quantum teleportation is as follows. And all we have to do is we prepare a message qubit here. Here, I just prepare an arbitrary message qubit. It's not very important what it is. It's just to demonstrate that we can actually obtain the same state of this message qubit as the outcome of measurement of Bob's qubit after the teleportation protocol. So this portion of the circuit here is actually the Bell pair that is constructed between Alice and Bob that we see here. And then this portion of the circuit is the message qubit that she creates. The C0 that we see here is what allows Alice to entangle her message qubit with her half of the Bell pair, right? Of course, this last qubit we'll just call Bob's qubit. It's Bob's qubit. Then she applies the Hadamard gate to the message qubit. And of course, what you're seeing here in this circuit is what we would do to run the circuit in a quantum computer. But after this Hadamard gate, what usually happens is when we have a classical channel, at this step here, we measure this qubit and Alice's qubit. And depending on the outcomes of measurement, we will tell Bob what to apply to his qubit. So for example, if Alice measures her 2 qubits and she gets the outcome 0, 0, she can tell Bob, don't do anything to your qubit. It's already in the same, it's already in the message state. But if Alice gets the state 0, 1, then she'll tell Bob to apply just an X gate to his part of the bell pair, just to get the same message, to get the same message, the same state as the message qubit. If they get the state 1, 0, she'll tell Bob to apply the Z gate to his qubit, and the state 1, 1, then she'll tell Bob to apply X and then apply Z to his qubit to obtain the message qubit. And if you follow this algebra that you see here, and after you do some factorization, what you'll actually see is that if you apply the X and the Z gate, you'll end up with the, so if you're in 0, 0, you do nothing, and you end up in the same state as the message qubit. If you have 0, 1 here, then of course you need to apply X to the message qubit to get the same state, and so forth. And you can follow the operation. You'll see how Bob ends up with the same message qubit that Alice created. And of course, this should be known that quantum teleportation doesn't violate the no cloning theorem and stuff like that. So this is a perfectly quantum mechanically legal way to, send the state of a single qubit. Not send, but I put send in inverted commas, but it's a way to replicate the state of the message qubit on Bob's qubit without violating any of the no cloning theorem, etc. The syntax for the circuit is the same. We've seen these gates in both lectures, so you can actually construct this on your own if you're interested, and also play around, create your own message qubit and follow my analysis to see if you actually did obtain after the measurement the same state in your in Bob's qubit. So once we construct our quantum register and classical register, we construct the circuit, which you can see here, and we run it, but we'll use the QASM simulator. So here I will use 100,000 shots in the QASM simulator. That's to get the most accurate results. So we have a large number of shots in the experiment. This will converge very nicely to the actual values. Once I run this circuit, I obtain a list of counts. Now, it's important to note that Qiskit uses this little Edian notation. So you read classical bit strings from right to left. So the qubit that's on the leftmost classical bit corresponds to Bob's qubit, or the state of Bob's qubit after measurement. So once we have this count list, we can plot it on a histogram, as you can see here, and we can use the outcome of the results in these histograms to actually check if we actually teleported the state. And the way to do it is, first we need to actually see what did our message qubit state look like, because if you recall, I constructed an arbitrary one by using the U3 gate and construct some message qubit. We need to see what does the state vector look like of just the message qubit on its own. And we can do that with the state vector simulator. So we just call the state vector simulator, and we have a quantum circuit with just one qubit to just see what the state of the message qubit looks like. We apply that same U3 gate with the same parameters to the circuit. We execute it, and we see that the vector we obtained is as follows here. That's the state vector of our message qubit. And if we want to see what's the probability of being in the state 0 of this qubit, we would just do absolute value squared. And as you can see, probability of being in 0 is just 0.95. It's approximately 0.95, and it's approximately 0.049 for being in the state 1. Of course, the way we can actually check if the teleportation algorithm was successful was we look at all the times when Bob's qubit, this being the qubit to the most left here in this, the bit to the most left was counted to be 0. And we sum up all of those probabilities. So we look at our histogram and we see that these first 4 bars in here actually correspond to Bob's qubit being in 0. So we need to sum up these 4 values, and that will correspond to the probability of measuring Bob's qubit in 0. And when we actually sum it up here, we see that we get 0.951. And to check the probability of Bob's qubit being in the state 1, we just need to sum up these probabilities, and we get 0.049. So here we see that, of course, it'll only converge these values in if we have infinitely many shots, but we see that we've fully teleported our message qubit state to Bob with the teleportation protocol. So this is a very interesting application of quantum computers and quantum computing, in that we can use these very simple operations that we learned about to actually do something very non-trivial by leveraging quantum entanglement to actually teleport a message qubit state from Alice to Bob by making use of the entanglement between the qubits in their bell pair. Of course, as I said, we don't see the classical channel we measure and then transmit to Bob in the circuit. We just put in these gates, this control X and this control Z, which is keeping everything in a quantum circuit. But as I said, in the real world, the way you would go about doing this is you would measure and then send that information to Bob through a classical channel. And of course, the reason why it's secure is because all Alice would be doing is just sending Bob 00 or 01 or 11, and he would have to then apply operations to his qubit. And even if somebody picks up that information through the classical channel, they can't do anything to get the message, because just knowing 00 doesn't actually give them access to the message, because Bob has access to it through the entanglement of one half of the bell pair that he shares with Alice. So that's basically the teleportation protocol. And at this point, I'll take any questions that you might have. Yeah, so, and that's basically all I want to cover for today's Mini-School. No, it does not teleport the quantum state faster than the speed of light, because again, we're not moving the quantum state anywhere. And of course, the information that we send over the classical channel is going to be bounded above by the speed of light, of course. So yeah, the speed of light is universal speed limit. Nothing moves faster than the speed of light.
Yeah, Ian, thank you very much for the very nice lecture. I'm sure it was useful for everybody.